So last time we studied work and energy. Okay. So what you learned was if you want to transfer energy to this object, from this object to that object, this object would have to do work on this object to increase its energy. Okay? So for instance, if this object did work on that object, and if that object, that work done was greater than 0, you increase the energy of this object. Conversely, if you do 0 work, you haven't changed the energy of the object. If you do negative work, you decrease the energy of that object. Okay? Then we learned how to do work. Okay? So the message is to do work, you need energy. So if this was you did positive work, the energy of this guy decreased, the energy of that guy increased. And all that happened was in the act of doing work, energy got transferred from here to there. Okay? So the reason I'm mentioning all this is we will see what is our source of energy currently, because we are always looking to do work, and then when you do work, you're just transferring energy from one object to another. Okay? So we learned how to calculate work. Okay, so if the object moved in a straight line and if the force was constant, what do I mean by the force being constant? As the object is changing position as it's moving, the force acting on it remains the same. Okay, so for a constant force, the work done was this dot product. Okay. And that was one of the reasons why we learned how to take dot products of vectors. Okay. All right, so we learned that. And then the next thing to do was, what if the force is changing? How do you calculate the work done? Well, then you did the following smart thing. You just broke up the displacement into little pieces. Okay. F cosine theta is the component of the force along the displacement. Okay. So that is Fx dx. Okay, and then you summed over all of that. Okay. That was the work done. And you call that the x component of function of x, dx. So for a constant force, that was the work done. When the force changes, the object is still traveling in a straight line. When the force changes, the work done is that integral. Okay. So you learned all of that. And then the most general case was a non-linear trajectory, and the force is also changing. Okay. But then you learned that so you could do the line integral to get the work done. Okay. So you learned how to calculate the work done by a force in the most general case. Okay. Now today so you learned all of that. Today what I'll do is, this is a little bit of extra information, but it's important information for you guys. Okay. So we'll learn about this. Okay. Now the numbers are really very fast moving in this field. So the numbers give you a sense, they might not be the latest numbers, but they're in the ballpark. Okay. So you learned in this chapter you need energy to do what? to do work. Okay, so let's see, where does the world get its energy from? Okay, what this graph says is, so this is this is roughly true 5 years later. The total amount of energy the world uses is 600 exajoules. Okay, so 600 into 10 to the power of 18 joules per year. That's how much energy you need to run the world in 1 year. Okay. And we'll see where the energy comes from. Okay. All right. In this business, now, so this is how much energy you need in a year. Now, of course, the energy is not steadily used in the sense that if you look at how much energy Daytona Beach uses in a day, or the rate of energy consumption, during the day it's higher, lower. So this is at daytime, nighttime, and so on. Okay. So for instance, okay. But right now we'll see, let's say if the world uses the energy steadily, how much energy, I mean, what rate of power, what power you would need. Okay. All right. A gigawatt is, that's that, billion watts. Okay, in the US, to run your house, you need about 1,500 watts. Okay, all the refrigerators and the air conditioners and all that run. Okay, and that's a small to medium sized house. The energy consumption is going high. But let's say you need 1,000 watts to run a house. We'll just keep it simple. So with a gigawatt, you can run 1 million homes. Okay, so that's to put it in perspective. Hoover Dam is a gigawatt. So let's say on the average, it can produce, if there's more water and you open up more gates, you can produce more power. But let's say a Hoover Dam is a gigawatt, and that's a large power plant. Okay, so the cost to build a Hoover Dam today, it'd be many billions of dollars, 10 to 15 billions of dollars. But a gigawatt of solar power is about $3 billion. Okay, maybe a little less, depending. All right, so anyway, what you want to think of is roughly this is $3 to $5 billion. Okay, to run a plant and to build a plant like that. Yeah. All right, I'm just giving you numbers all over. Okay, so this is how much energy you need to run the world in a year. Okay, that's how much energy you need in a year, and in a year, that's how many seconds there are. So joules per second, that'll come out in watts, and we'll divide that by a Hoover Dam. That tells you how many Hoover Dams you need to run the world. So this number, okay, is roughly, so 16,000, okay, so we'll say roughly 15 to, you need that many Hoover Dams running constantly 24/7 to run the world. Okay. Now, of course, I mean, the energy use is not constant, but we won't worry about all of that. Yeah. All right, where are we getting our energy from? Today, we're getting most of our energy from fossil fuels. Fossil fuels are coal, oil, and natural gas. Yeah. Why are we getting it from there? It's cheap. All you have to do is pump it up or dig it up. Okay? So it's cheap. Well, what is the problem with that? And what are the renewables, by the way?
Solar, wind, water.
I'm sorry?
Solar, wind, water.
Yep. and nuclear is also in there. Okay, but anyway, all right. So, all right. So these are our energy source. We need energy to do work. The problem with fossil fuels is whenever you burn the fossil fuels, you're putting CO2 in the atmosphere, and this is a greenhouse gas, and this is the problem. And so for your generation, this is the biggest problem. Okay, and that leads to global warming. And we'll talk about this and what does this mean. So that's the biggest problem facing you guys. All right, so hydrocarbons are compounds that obviously have hydrogen and carbon atoms. So here's the simplest hydrocarbon, methane. This is natural gas, 85% of natural gas. And the way you get energy is you burn it. Okay. That's how you get energy from anything. You burn it, oxidize it, you produce carbon dioxide, and this is the problem. Water and energy. All right, now this energy, the best you're doing is, so that energy is released as heat in your car, you're using it at 20% efficiency. In a power plant, you're using it at 40% efficiency. Okay, those guys are big boys, so they can use at a higher efficiency. You burn at a higher temperature, you use it at a higher temperature. Okay. So only about roughly a third of the heat is converted to electrical or mechanical energy. The rest is wasted. All right, now let's talk about what is the problem with CO2. Yeah, that's one of the greenhouse gases. Okay, so here's the deal. Okay, if you were around about 300 years ago, the average temperature of this rock, the surface average temperature of this rock, was about 14 degrees Celsius. Today, it's about 15.3 degrees Celsius. Okay. Your goal is to be below 16 degrees Celsius. Okay. Now, how did we get from here to there? Okay. You guys following this? Okay. All right. If you want to warm this, okay, well, here's what's happening. Okay, so here's the atmosphere. There's our atmosphere. We're getting energy from the sun in the form of visible light. The wavelength that you receive will depend on the temperature of the object. Okay, so what you're receiving is this. So this is the intensity, this is the intensity, and this is the wavelength. This is what you're getting from the sun. And then the earth warms up and you emit infrared radiation. Because of your temperature, this is what you're emitting. Okay, now for if you don't want to warm up, if you want to maintain a steady temperature, what should be true?
Energy in equals energy out.
Very good. Whatever you're getting in, that's what you want to emit. What that means is the area under this curve should equal the area under that curve. So if you emit less, you'll warm up. If you emit more, you'll cool down. All right, today you're emitting roughly 3.25 watts per meter square less. Here's a meter square. For every meter square, you're emitting 3.25 watts per meter square less. So you're warming up, and that's what's happened. Okay, that's the number today. I mean, it's grown over time, and we'll see why we're emitting less. Yeah. Now, I'll give you a number that has a little more shock value. This number is sort of innocuous. It doesn't give you a sense for what it is. Okay, what this number amounts to is, do you guys know the atom bomb that was dropped a few years ago? Yeah. In Japan, Hiroshima. You didn't hear the explosion? What this number means is you drop 20 of those every second. 24/7, 365, and trap that heat. That's what that number means. All right. Right, so now we'll see, why are we radiating less? If you were here in 1750, what you were getting is what you were radiating out, okay? Okay. All right, so why is that happening? Because we're changing the properties of the atmosphere. Okay. In 1750, what was coming in, what was going out was equal to what was coming in. Okay. And today, what's going out is less than what was coming in. And why did that happen? Because we changed the property of the atmosphere. And what did we do? We put CO2 in the atmosphere. Okay. And what CO2 does is, so you emit infrared radiation. CO2 is transparent to visible light. It doesn't care about visible light, but it sees infrared light, so it'll absorb infrared light and it'll emit in equally in all directions. So essentially, the infrared light gets trapped, and so you're warming it. Okay. So, well, what happened? So, like I said, we've changed the property of the atmosphere. We've changed the atmosphere in 1750, and again, these are rough numbers. The amount of CO2 was 280 ppm, parts per million. Today, it's about 420 parts per million. So we've increased CO2 levels by 50%. Okay. Now, the greenhouse effect is not all bad. So, for instance, if there was zero CO2, the Earth's temperature would be minus 18 degrees Celsius. That's what this is saying, okay? With 280 parts per million, it's 14 degrees Celsius, which is good. We like that. What we don't like is 16 degrees Celsius. That's bad. Okay. And the carbon CO2 levels are increasing. Okay. So the current temperature is about 15.3 degrees Celsius. The goal is to be below 16 degrees Celsius. Well, for a while there we were saying 15.5, but that's not likely to happen. Okay, so what this graph shows you is, so this is the radiation coming in, and this is what we're emitting, and this is what would get to space if there was no CO2 in the atmosphere. And you see the CO2 is absorbing those wavelengths. So radiative forcing, what that means is what is coming in minus what is going out. And so the radiative forcing is 3.25 watts per meter square. Okay? And that amounts to exploding 20 atom bombs every second and trapping the heat. What's that?
That's a lot of heat.
You guys know about Lake Superior? It's one of those little lakes. And in the winter, it freezes over. A 1.5 meter layer of ice forms. 1.5 meters is roughly my height. And so you have to remove heat to freeze water. And you're removing heat roughly so that's how much heat you're removing to freeze that one lake in the winter. Okay. So nature does move a lot of energy back and forth. Okay. And then it'll put that energy back to melt the ice in the summer. Okay. All right. Now, the thing is, once you put in the CO2 in the atmosphere, this graph tells you how much the warming lasts. So roughly, the carbon dioxide lasts in the atmosphere about 100, 120 years. Yeah. So the problem doesn't go away easily. So this graph shows you, see, this is 10,000 years ago. See, that's about 25. So the CO2 levels have been roughly about, this is 280 parts per million, okay? So for the past 10,000 years, CO2 levels have been 280 parts per million, and then they've shot up in the last 40, 50 years.
There were no cars 2,000 years ago.
Yep.
There was no one trying to change the atmosphere 10,000 years ago.
Yep. Hey, it's not going to be my problem, it's your problem, buddy. I'll be dead.
Well, we could say the same thing. It's not gonna be my problem, it's gonna be, my kid's problem.
That's right. Hey, you can see, I'm just,
Yeah, exactly. How about it's all of our problems, yours and yours. You help us, we'll help you.
no, I care about it. That's why I'm telling you about it. Unless you understand the problem, how the hell are you going to solve it? Anyway, all right. Okay, so you have to be careful about these terms. Okay. So when you see the numbers, they'll say how much carbon you dump and how much CO2 you dump. So the world is dumping about 40, again, these are roughly billion tons of CO2 per year into the atmosphere. Oxygen weighs 16, so that's about 32 atomic units. 32 plus 12, 44. Okay. Carbon is 12, so it's 1/4 that. Okay. So the world is roughly dumping 10 billion tons of carbon per year in the atmosphere. Okay. You can say it one of two ways. How much CO2 are you dumping? But it's also said as 10 billion carbon is being dumped, billion tons of carbon is being dumped into the atmosphere each year. Okay. So since the Industrial Revolution, we have dumped 500 gigatons of carbon. Okay, 500 gigatons of carbon in the atmosphere since the Industrial Revolution. The amount of carbon we are dumping has been exponentially rising. Okay, simulations suggest that another 500 gigatons of carbon can end up in the atmosphere. You potentially, I mean, maybe this is an optimistic number. Anyway, so let's say the sky won't fall down if you dump another 500 gigatons of carbon. So at the current rate of 10 gigatons, you can maintain status quo for another 50 years. That's assuming your simulations are right. Okay? So we can act irresponsibly for another 50 years. So here are, again, these are simulations. That's where we are today, 420 parts per million. Okay, so what this is telling you is change in temperature above the pre-industrial level, which is 14 degrees Celsius was it. Remember, your goal is to be below 16 degrees, so you don't want the temperature to rise there. Okay, even with the current level, there is the temperature range predicted in the future. Okay. What if the temperature rose by 2 degrees Celsius? What if we get to 16 degrees Celsius? Okay. Again, these are rough. So if you get to 16 degrees Celsius, Greenland, all of Greenland will melt. There's no turning back. And that'll happen over a time scale of 3 to 10,000 years or whatever. And if that happens, if all of Greenland melts, sea level will rise by about 7 meters, which is roughly a little 1.5 times this. 7 meters, if it rose by 7 meters, okay. About 10% of the world's population, 800 million people, live along coastlines less than 10 meters above sea level, that all have to move to higher ground. Okay, so you'll be affecting a lot of people, and you know how the weather has been changing and stuff like that. Climate has been changing. Okay, is there a solution? Yeah. I mean, if a problem doesn't have a solution, then we're all screwed. So the question arises: is there a solution? What do you need to run the world? How much? 16,000 Hoover dams. Okay, that's a terawatt. Terawatt is a gigawatt. Okay, so 16,000 Hoover dams is what you need to run the world. Okay, so there's how much energy, power you need to run the world. This is how much sunlight is falling on the earth. This is how much wind resources are there. Okay, so just between the sun and the wind, you can easily satisfy the energy needs. And here's the kicker: this is how much you need to run the world today, with 80% of it coming from fossil fuels. Fossil fuels, remember, you're only 1/3 efficient. So if you were getting all your energy in electricity, you would need a lot less to run the world. So if you were getting all your energy from the sun and wind, you could easily run the world. Okay. What this graph shows you is, okay, so 900 terawatt years. So let's say in the future, if you get all your energy from coal, 900 divided by 1615 is is what's 15.6. You could run the world for 60 more years if all your energy were coming from coal. That's what that means. 900 terawatt hour a year divided by 15 terawatt, this number. You could run the world for 60 years. That's what those numbers mean. Okay? Anyway, so for your sake, we have a solution. You can run the planet just on solar and wind. Okay? In fact, all you have to do is harness 1 part in 10,000, roughly 1 part in 10,000 of the solar energy reaching Earth. Here's a pretty picture. This is 300 kilometers by 300 kilometers. 300 kilometers by 300 kilometers is roughly from Melbourne to Jacksonville. So imagine solar panels that big, square solar panel. All you need is 6 of those to run the world. All right, what this is showing you is in 2012, see, most of the energy was coming from fossil fuels. It's still true. And as the world transitions to renewables, okay, so this is a simulation by a group in Stanford. Okay. By 2050, what they say is about 40% of your energy will come from wind energy, and about 60% will come from solar energy. And this is with existing technology. You don't have to invent new technology. Yeah. So if you had the same current mix, you would need 20,000 Hoover dams to run the world back out then. But if you're running on renewable, all you need is 12,000 Hoover dams. That's because when you produce electricity, when you run the world on electricity, you're more efficient. The Tesla car is about 90% efficient, while your gas car is 20% efficient. Oh, let me restate that. An electric car is 90% efficient, and a gas car is 20% efficient. Like I say, it will be all your problem to solve.